Okay, good afternoon. So I think it's 12 o'clock. We will proceed with the class. All right. Anything you guys just text me on chat room. I will check every probably 10 minutes. The first 10 or 20 minutes I will check. If anything you guys text me cannot see or whatever because this ultra thing, it's very inconvenient because you cannot see other people's chat and do your lecture at the same time. All right. Okay. All right. I think last week we've discussed, I think, about mostly concentrated on the CPU. Okay, so a bit of recap: CPU, ALU, and status register. We've covered status register. This is one of the main stuff. Status register. They can ask you a lot of questions. Status register. Give me some feedback, right? What you guys feel that you don't understand or whatever, so that I can change my tutorial on the spot. I don't have a fixed tutorial. I depend on what are students struggling with, and I do the tutorial. I design tutorial based on feedback. Anything that you feel that it's very difficult for you to understand, just send me a email. I will see how I can change the tutorial to better benefit all of you. Special registers, stack pointers, all those are actually very important. Probably we will have some further discussion on that. I think yeah, it could be very important. Not everything is important, whatever I discussed, but certain things that are important I will actually highlight. Now this week, after we've covered the registers, ALU, etc., etc., and this week we're going to talk about memory. All right. So memory is a very important element in the microcomputers lectures. Why is it important? Is because memory CPU doesn't function. Okay. So if you all recall from the very first lecture that I presented, the memory is important in such a way that all the instructions when you program a microcontroller or computer, they are essentially stored in memories. Okay, and the computer cycles actually through the computer cycles, the CPU actually extract the various instruction set. Whether it's a RISC or sys instruction set, doesn't matter, and they will execute the instruction sets sequentially. That's where all the instruction register, stack pointers, program counter, all these kind of things actually play a part. So those are the stuff that we've discussed last week. I hope that you guys put some effort to understand the flags. I've made some effort to discuss more on flags because I feel that that was something that was lacking last semester, last year, same unit. And this year, I actually want to reinforce on this area to enable you guys to understand better about flags, right? So this week, memory organization, we will discuss. We know that roughly they carry instruction sets, and the CPU actually communicates with the memory via integrated logic to the various buses, the memory buses, and etc., etc. So memory very important. We're going to discuss. We're going to discuss. There are a few things that we're going to discuss. Okay, not everything here is important. There are 5 things that we're going to discuss. I want you guys to focus more on a little endian and big endian, okay, conventions. That's where some of the questions can come out, very tricky questions. The rest are basically just reading material. So little endian, big endian conventions, very important. they can actually ask you, given a word or a byte, what will happen to the memory. Okay, so that kind of stuff will actually come out. The rest are just reading materials. It's just like something that you read. You can check out other information, Wikipedia, whatever, textbooks. Okay. Little endian, big endian conventions important because these are calculations and application matters. All right. Now, a quick overview. I actually have 40 slides today. A bit rushed to cover everything. We see how it goes. All right. Memory overview. The memory system stores instruction and data that we know. Okay. So I've actually explained. You have instruction sets. Okay. When you do a programming, the compiler saves the instruction in the memory. Okay, so if it's a microcontroller, the memory will be in the same die. And also data, all right? So when you run a program, you generate data. So data are the stuff that you generate, like for example, okay, in a tutorial, we try to solve a lot of stuff, like for example, 4C plus 5D, So the answer will be stored in temporary memory or register. So this is what we call memory subsystem for data. For instruction, very straightforward. The program that you write, okay, you use a compiler to generate, and you have a memory instruction set stored in several memories. That's where you have all this kind of instruction register, program counter, trying to figure out, sequentially help the CPU to extract the information one by one. I'll check the chat room. Anything that okay, I'm checking the chat room. Okay, no chats. Okay, no chats is good, so I'll proceed. All right. Okay, so memory subsystem stores instruction set and also data. That is something that we need to remember. Memory consists of a large number of hardware components which can store 1 bit at a time. Looks very simple, but something very straightforward. Okay, these bits are organized in n-bit words, working as a single register, which is usually referred to as a cell or location. So you can look at memory as a cell or location. When we want to ask questions on this, typically we draw a box, and then we call this box some address. What is inside this box? All right. So we can visualize this as a cell, okay, or a box or a location. Okay. So contents of cell is a basic unit information called memory word. All right. So the contents are actually called memory word. Each memory location is identified by a unique identifier called memory address. Now, this is important, okay? Now, each of this memory you can access. Let's say, for example, you have a 16-bit memory location, okay? Now, a quick one, 16-bit memory location. So, how many hex, how many hex symbols does this address have? So you have 16 bits, hex is 4 bits. So you have 4 hex. The memory of a 16-bit address can be represented by 4 hexadecimal value. All right. So if you have an address, okay, let's say for example, you might not know it, but your pen drive memory system, okay, you can access it. Sometimes we do projects using microcontroller, and we might need additional memory. So we have this thing called EEPROM. That's where you need to read the information from the memory. Okay, so if the EEPROM normally in 16-bit address, means to say that 16-bit address, you can imagine 2 to the power of 16. All right, that's how many cell locations that you have. Okay, 2 to the power of 16. All right, so memory consists of m cells and n bits. All right, so you have let's say for example 2 to the power of 16. That's the number of cells that you have, and each cell consists of probably 8 bits. generally, all right. Some memories have 16 bits, so on and so forth. So if I said, you know, I have a 8-bit memory system. 8-bit memory system means 2 to the power of 8. That's very little. Okay, so those days we use their pen drive that have very small memories. It's a regret that actually I did not keep one of these pen drive. They are normally very big size. Okay, and the memory is very small. You put 5 or 6 picture inside, you know, the pen drive, essentially it'll be full. Okay, so M cells and bit. When you have 2 to the power of 8, that's the number of cell you have, and each cell can have n bits of memory. Okay, so that's why memories used to be very small. Now, if you go to certain shop, I was looking into a gigabyte range pen drive. That's the number. That's how memory have actually advanced over the years. Small package, you have very big memory. Okay. Now, this picture depicts everything very clearly. You have your CPU at one side. Okay. You have a CPU at one side, and then you have your address bus, memory bus, control bus, whatever bus you have. Address bus is basically you want to locate that portion of the memory. You need to send the address to the address bus, and this address bus will communicate with the memory. Control bus, read-write operation. Okay. Data bus means the information that you want to extract or write. Okay. Now, give you an example. This is the memory. CPU inside you have your logic interface with all this kind of bus, call it BIL, bus interface logic, and this is the information to and fro. You realize that this arrow is always one direction, but in the case of data bus, it's 2 direction because information can travel both ways. But address bus is always CPU wanting to access a certain memory. Okay, and then you have your control bus. Control bus is of course to determine which chip or whether it's a write or read operation. Okay. For example, in the previous diagram, the cell address 0FFF hex contains the value 20H. So this is the value that you want to extract, or you want to extract because you already said that this 00 FFB6, all right, is in this location. You want to access it. The CPU will send the address. Control bus, okay, will do the necessary. Most probably is a read operation, looking at the description, and then this information will be copied up to the registers in the CPU for operation. Okay. Okay. Now there are 2 ways of showing the content. Okay. This is the way we actually write. How do we represent this content? Our way of expressing this operation. Okay. So we can say in a bracket FFF equals to 27H. So this is how we write. Okay, the contents of FFF hex equals to 27H. Now 27H, you know that the address is 16 bits, but the content is 8 bits. All right, so it's an 8-bit content. So this is how we formally write, how we express our idea. Okay, our statement. Okay, so FFF hex equals to 27H means to say that this is a mistake, right? Short of 1F. Don't worry about it. At least you know. Okay. So FFF equals to 27, but in a bracket means to say the location, okay, as expressed by this hex value stores 27H. We will have more discussion on this. This is what we call addressing mode. How do we address? How do we convey this message? There are several ways to do it in a programming language. Okay, and one of this way is called the this is one of the methods. Okay, so this is, if I'm not mistaken, immediate mode, addressing mode. This is how we express this statement. Okay, the memory location contains this value. Hardware. Now we always think about, in our discussion, we always think about memory as just a block diagram. Okay, memory. But if you're really to design a system, let's say for example a pi or something like that, then you have the memory is classified as based on the storage permanence. How long can you store the memory, okay, and the write ability. Some of these memories, they have very low write ability. You need very high voltage, and you need a very long time. Most of these systems, they are either electromagnet or ferroelectric or something like that, okay. So that makes it difficult to write. Storage permanence, you have information in memory. How long does it can it last? So in a volatile memory, volatile means, in English, volatile means something that's very easily destroyed. Okay, you read, what does it mean? This word means that it's very easily destroyed. Call it volatile. Okay. Now, in a volatile system, all you need to do is just off the power, all the memories will be gone. Okay. So in other non-volatile memory, you have maybe whatever that you store inside. For example, a good example is pen drive. Okay, I store my information inside. How long can the information last inside the pen drive? Okay, 10 years, 20 years, 25 years. I have no information on this. It's basically depend on the technology that they use. You can read up more about it. Write ability. So we want low voltage, right? Okay, so it's best to have low voltage, right? So that in any process, we save power. So V equals to IR. So and power equals to VI. The higher the voltage that you need to write this guy, the more power is consumed. So that's an optimization issue which we need to take care of. All right. Okay, so like what I mentioned, non-volatile and volatile. Volatile means you off power, everything is gone. Non-volatile means you off the power, you still have information. All right, so you can use any material to design memories. You have an idea, okay, I want to use garbage, okay, garbage-based material or recyclable material to develop, all this kind of thing. Then well, you found out a way to actually utilize, whatever garbage. Most of this technology use ferroelectric, volatile. Most of them use flip-flop. That's why they are. Once you unplug the power, everything is gone. Okay. So if you figure out a new material to design memory, that's a good challenge. All right. Especially materials that are actually abundant. Okay. So ferroelectric material, it's abundant. Okay, you can think of other way. Of course, any chemical method of storing information, it's out of the question, because you can't fit chemical-based memory into something that's so small package. Okay, out of the question. Think of something that small and it's easily erasable, okay, with the right amount of voltage. So people are still constantly looking at memory system. Okay, we come out with a memory system that is based on this technology, based on that technology. The challenge is, how can we find a cheaper technology with low writability, means to say that very low voltage I can write, okay, to ensure that power consumption is optimal. Okay, write ability. When we say write ability, what do we actually mean? Write ability means this system can be written by the processor, write-only memories. This group is divided by the following: write or and read, or in-system programmable, read-only base. So when we mention this word, it actually means that you can have a write and read operation, or you can have only a read operation. Of course, you don't have a system where it's write only operation. That will be a very stupid system, because the normal memory is that most of this memory we want to read what's stored inside the memory. Okay, so it could be a permanent, something that's written permanently. People like permanent memories because manufacturer, they might write something on a permanent memory, and then all you need to do is just read. They do not want user to actually do something. Okay, so long time ago there was a friend of mine that saying, oh, how can we actually well, this is not good, but think about it. Something that's written in the memory, how can we actually extract out, if the device is partially damaged, all right? So how can we extract out this information? So this is something that some people ask me, memory partially damaged. How do we actually extract this information? So this is a very big topic. Okay, extracting information from memory that's partially faulty. It's a very good technology. Figure it out how to do it. So writability, it's two categories: write read or only read. Okay. Now, most volatile memory like SRAM, DRAM, volatile memory can be written during the program execution. So these memories are useful for temporary data or data that will be generated, modified by the program. These are like whatever that we did in the tutorial. Okay, we did an operation. The answer will be stored in temporary memory. Most in-system programmable non-volatile memory are written only when loading the program. Okay, so you have a system that's volatile, non-volatile. Okay, volatile normally for memory, temporary memory, registers, and so on and so forth. Non-volatile, you need something that's after you unplug the power, the content will still be there. Okay, so okay, very simple question. Arduino Uno. Okay, like for example, Arduino Uno. If you after you program, you need to unplug the power. You cannot let the power stay forever. Okay, like for example, my house a few days ago, Senadian and this Lutong area, their power cut off. So there is this device. There is this alarm system. Okay, you need a battery, a coin battery, to maintain what's in the memory, the settings, and so on and so forth. So these are actually they store it in a volatile memory. Okay, probably they put a coin battery just to maintain it. So that's a very sustainable way of doing it. They do not want to use a non-volatile memory system, so that will be more expensive. Okay, but you can use a coin battery. Anything that has a coin battery means to say that they have some form of information in the volatile memory. Okay, so they need power to maintain the memory. Okay, so that's how we differentiate. Now, non-volatile will have a problem. Writing speed is too slow for the program. Okay, in case of you cannot use non-volatile memory for stuff like registers and ALU operations, because they're too slow. All right, so you might need a second, to write a few kilobytes of memory. That's actually too slow. Okay, but writing in, let's say we write in a flip-flop. Oh, that's very fast. Okay, so writing in flip-flop is very fast. Okay, give you another example. Nowadays, I think I went to the shop and I reprogrammed my PC. I bought a regular hard disk. All right, so that's a form of memory. That's a form of memory, but not exactly what we're discussing. All right, and then somebody was actually suggesting, why don't you get a static, hard drive, static hard drive. Okay, now I know that of course static hard drive will be much faster. There's no rotating equipment, no nothing. It's just a static device. All right. There's no motor running. Okay, so static device works like they have a slightly higher writing speed compared to the normal hard speed, because hard disk is because they are static device. They do not have running motors and whatsoever. So it's very it's just depending on the how fast you read, and it's much faster. You on your PC straight away, the information, the OS will load, because the writing speed is much faster. You can take this concept and try to, if you're designing a microcontroller, microprocessor memory in the future. Okay, so which one will you choose? The spec with the highest writing speed or the spec that is the cheapest? It's up to your design constraint. All right. Some unique characteristic. Now we're discussing this particular non-volatile memory. They call it FRAM. Okay, flash. The writing speed of FRAM is comparable to DRAM. Unlike flash or DRAM, only consumes power while writing and reading. So it is very low power device. So this is recommended. You only consume power when you're writing or reading. Very low power device. So this memory system is actually good. We will cover all this. What are these FRAM, DRAM, all this stuff that we are very foreign to us. All right. In the embedded system, check again your. Let me check any chats. Whether anybody has problem accessing. Okay. Oh, that's good. Okay. In the embedded system community, volatile memory are sometimes referred to as RAM, while ROM is used for non-volatile. Okay, so this is the typical convention. People normally volatile and are sometimes referred to as RAM and ROM. Okay, so even your computer, they use the same terms. All right, RAM is the term coined in 1950s to refer to solid state memories that use access memory as opposed to magnetic disks or tapes. All right, so hard disk is running on a motor. Okay, so that's more magnetic disk. All right, so that's why we call it hard disk. But a RAM is a static device. There's no running motor. So it's much safer if you travel around. You use a static device. Okay. So be very well seeing the term RAM and ROM when it comes to embedded system. Just understand system. All right. So this table is very good. It gives you straight away. It shows disadvantage and advantage. Some have the writability is a yes or no. So because everything can be read, of course, some cannot be written to. They can only be read. All right. So this in system writable actually means that some system you can only read, some you can some you read, some you can write and read. Okay. So this is the category. Subsequent 8 or 9 slides we will discuss one by one. This is the comments. Some are not programmable, some are programmable, some you need to actually burn it. Some can only be used one time. All right, we will discuss this in the subsequent slides. Okay, now look at this mass ROM. Mass ROM is something that from this table is non-programmable. Okay, it's something that being used in the early years. They are actually used in some of these equipments. I think yeah, this is a very old device. Okay, so it says non-programmable. You can only mass ROM. You can only read. You cannot write. Okay, so this is useful for system where you do not want the user to interrupt or do anything, or to find out, or to reverse engineer your system. So this is a very good device, non-configurable. Okay, once you put the information inside, it's not programmable. Okay. This is an example of OTP ROM, one-time program ROM. It's permanent and cannot be changed. Okay, so you're very familiar with one-time program. Means you can only write one time. Okay, it comes in you need a special device to actually write. There are probably some signals that you need to apply on one of the pins before you actually write. And once it's written, you cannot actually remove the information. So this is something very useful again, if you do not want the user to actually reconfigure your system. So it's very useful. It's designed by Texas Instruments. So the code is TBP18SA030N. Yeah, some of you might want to consider this for your FYP projects in the future, you want an external memory. Okay, again, looking at this chip, I do not know how much memory it has, but this is something that you can use. Okay. Once program and EEPROM, example, erasable program. Okay, this is an erasable programmable ROM, can be erased by exposing it to a strong ultraviolet light source. Again, this device actually is in your click tree board. Okay, this is the memory system that we have in the click tree board. The device that you have in your app. Okay, again, take this opportunity to explain a bit about the lab. The lab sessions, you do. I hope that I sent through the Moodle, how to set a VPN and how to go inside remote access. Okay, so there will be a device that once you load the program inside, you observe it starts on Wednesday. So we've been doing testing for the past 1 week. I think it works. So you guys can access the information in the Moodle regarding this lab. Okay, you're supposed to choose. I think it's 2 person per group. Okay, so this equipment that you see in the lab called Click3 is designed. They have external memory using an EEPROM, erasable. Okay, so you can erase what's inside. You can just reset whatever that's in this thing using a very strong ultraviolet light source. Okay, there is a glass opening, you know, that you can see on the device itself. Okay, and the way to actually remove all memory is that you can buy. You need a very strong ultraviolet light. Possibly those that to detect fake bill money, fake bill or money. Possibly that can, but I think the you need a higher intensity of ultraviolet light. Okay, so there's a glass bulb where you can shine your light, everything is removed. So this is very good for certain application where yep, you do not want the user to disturb whatever that's in your memory, but once in a while, probably every 5 or 10 years, you want to change the program. Okay, that becomes very useful. So it depends on how long you want the information to be inside. If your device wants information to be inside forever and ever, okay, and these two memory system will be much more suitable. But if you want to change something that's on the medium time scale, 10 years, 5 years, and this is something that you can actually use. Okay, electrically erasable programmable. This one is a good. You can apply probably a certain special programming signal. Like for example, if I apply the signal 1010, okay, on the one of the pins, okay, I can actually remove whatever content that I have inside. Again, this one is for medium range. Okay, I don't want people to keep on reconfiguring my memory, but I want to do it once in a while. In a while means probably 5-10 years. You know, I want to reconfigure it. This is very similar like your flash UV flash system, but this one it's easier. It's slightly easier to reconfigure because there's certain signals. Okay, probably in one of these tutorials I can bring this issue up. What are the signals that we're talking about for 24CO 26B6? Okay, so this is one of those EEPROM. Okay, and this is another type, flash memory. Okay, data can be electrically erased or reprogrammed. This is developed by Toshiba. Okay, EEPROM requires 2 transistors structure. Okay, so this again elaboration on whatever that we have here. You have different sizes. Okay, in the picture, flash is on the left and the controller is on the right. Okay, so yep, so this is actually talking about EEPROM, flash memory. Okay, has 1 transistor. This is something that we can discuss further, but so far I've never seen complicated questions on this part. It's just more for general purpose understanding how memories work. Okay. Ferroelectric. Okay, so so this the difference between DRAM and this FRAM is that it has the same function, but instead of dielectric, they use this ferroelectric. Okay. So this is another technology that you can do a read-write. Okay, so this is a read-write. Writability is a read-write. You can use this device to write information. Okay, so this is something that you use on you want to constantly program it. You normally use this kind of thing for devices where you want the user to continuously change the configuration in the memory, unlike the UV type, okay, where you seldom want the user to change anything. So this is more for reconfigurable memory system. You want to always reconfigure what's inside so that you can change your system setting. SRAM, static RAM, use flip-flops to store each bit. Okay, so you remember this guy is non-volatile, all right, and they use flip-flop. Once you remove the power, everything will be gone. Now this is a system where you need to use a coin battery to maintain what's inside. All right. SRAM stores each bit in a separate capacitor within an integrated circuit. So capacitors, you can look at capacitor like a battery. All right, it stores information. Okay, if you fully charge, you can be 1. 0 means it's not charged. So capacitors can be integrated into a memory system. So again, look something like what you have in your PC or in your laptop. Okay, those kind of RAM or memory system that you have. Now, most hardware memory nowadays are 1 byte long. Means to say that it's 8 bits. Okay, some very rare you will get other size like 16-bit or whatever, but it depends. All right. Each memory word has a physical address attached to it. So this is whatever that we've discussed. All right, in the previous slides. Each memory has a name. All right. So memory blocks that are 1 byte long are called banks. Okay. So you have a stash of memory. And they are 1 byte long, so we call this by using the term banks. If the data bus is wider than 1 byte, 2 or more banks are needed so that data bus can be connected. Now, if I have memory blocks, let's say for example 1 gigabyte of memory block that I've allocated for this system, and these memory blocks, each of this cell is 1 byte long, then we call this 1 bank. Okay, so anything that's 1 byte long is 1 bank. Okay, so if you have anything that requires 16-bit information, then you need 2 banks. Okay, so because information are processed using 4 hex. 4 hex means 2 bytes. Okay, so H1 not H hex, C1B5. Okay, so that's a 2 bank system, 2 bank memory system. Now, how do we actually cascade 2 banks to become 16-bit memory system? Now, look at this. This is something that you can do, complicated, but let's assume that you have a data bus that's 16-bit and you have a lower byte and you have your higher byte. Okay, so the bank system, which can only contain either higher byte or lower byte, will be cascaded together so that they can represent 16 bits. Okay, so the lower byte can be in the memory and the higher byte can be in the memory as well. Hold on. There is something is happening. Hold on. Okay, so this picture shows us how do we cascade 2 8-byte memory system to become a 16-byte. So you have 2 banks. You have, this is what we call the higher bank and what you call the lower bank. All right. So physical address is seen by CPU with address bus. Internal memories are addressed address proper to the bank. So you need a more complicated control system, okay, to access the high bank and low bank. Maybe while you're accessing the high bank, you use the control bus to enable the high bank, and then you disable the high bank and you enable the low bank. So your control system, control bus, have to be a bit more complicated if you want to implement something like this. Okay, again, if you have your information is of more than 1 byte, you have higher byte and you have a lower byte. So this is how you access the information. Okay, you do something to the control bus, do a bit of configuration, you can have 16 bits memory system. Okay, instruction longer than a byte. Okay, this is repetitive. Okay, so yep, this is just exactly like what we discussed. No need to go any further. Now this is something that we need to discuss. A word address and a double word address. Some of these system have such big memory system. You need a double word. A word means 16 bit long, and double word means 30 bit long. Okay, so sometimes you have 16-bit address system. 16-bit address system means 4 hex, and sometimes you have 32-bit address system, which is 8 hex. Okay, it's a very big memory system. Okay, now this is something important. I want you guys to familiarize yourself with this. Big endian means endian C. You see, most of this computer system, the terms, the terminology, they get these terms from whatever the early adopters of this technology, how they give the name to the terms. So apparently the guy who came up with this memory system, they are big fans of Aesop fables or stories. Okay, and in one of those stories there is this story about American Indian, you know, how they actually do things. Okay, and these programmers or early adopters, they based on the story, the characters in the story, they came up with these two systems. They call it the big endian and the little endian. These are just characters that they extracted from the stories that they love. So if you came up with a technology, you can name it after anything. Okay, so you can name it after Harry Potter stories or whatever stories that you have, you know, Monkey King or whatever. So if you develop the technology, you have the right to give terminologies to the technology that you develop. Okay. Now this little endian and big endian are just story characters. They are stories that these people love, and because they develop this system, they have the right to give names. Okay. Now big endian data is stored with the most significant byte in the lower address and the least significant byte in the higher address. So it's a bit like reverse order. Most significant bit in the higher address, least significant in the higher address, most significant in lower address. Okay, we're going to look into what does this mean. All right, but bear with me just for a little while. Okay, now this little endian, it's the direct opposite of big endian. Means to say that the lowest address and the most significant byte, okay, in the address. So the lowest address data is stored with the least significant byte in the lowest address and the most significant byte in the higher address. So look at this. Okay, now you have information that you want to write. Okay, so little endian will the information is 3428. Okay, 3428, like what you see here is 3428. Now little endian will write this is the higher address and this is the lower. Okay, higher, this is the higher and this is lower. Can you see 42FF is the higher address? Okay, 0302 is the lower address. Now look at big endian. Big endians means it stores the most significant bit in the higher address, the least significant bit in the lower address. Now look at how little endian do this in the little endian convention. 28 is stored in the higher, 34 is stored in the lower. So the most significant bit is stored in the lower address. 22 2B is stored in the higher. Okay, now This is if the information is 1 byte. Now, what if it's in the double word? Now, look at this information. It's very good. Double word means 9A267EFO. Now, look at how little endian will store. Now, little endian is the one that actually flipped the thing. Okay. Now, the lowest information, the lowest significant bit is stored in the highest. Okay, 7E, 26, 9A. Now, what about big endian? Big endian stores the most significant bit in the highest. Okay, so it's putting things in order 26, 7E, FO. So this is a double word. Okay, and this is a byte. So I want you guys to actually read more about this. This is very important. Okay, technical questions may arise from this. Okay, so word boundary refers to an event address, and double word boundary refers to address which are multiple of, meaning to say is ending with 048C. So this is something that you guys can read. Okay. The next column are words. Data is 16 byte. Okay, so this is another example of how does information, this EOF200410021. So this is how it arranged in little endian. Now you have a combination of word, double word, word, and byte. So even if you combine, okay, let's say this is the information you want to send through the computer cycles, okay, and this is what it will look like in big endian. This is what it will look like in little endian. Okay, a combination. Just now it's just purely byte or word. Now it's a combination. Now this is what it will look like. Now carefully go and observe. You know, why is it like this? Look at it a few times. You'll be able to get it. All right. Again, little endian is the odd one out. The most significant bit in the least memory system. The big endian, it's the one that follows the common sense procedure. The most significant bit in the higher memory system. Okay, the structure of microcomputers include two different memory. Okay, now this is something that we've just touched in the previous lectures. Program memory, data memory, I hope you guys still remember. Program memory means something, information that you generated in your program while you're doing your programming. Now, data memory means something that the programmer writes, is the memory that the programmer writes and stored in the memory. Program memory means something that is generated by running the memory. Okay, so a quick one, ALU operation, addition. Okay, you generated the information from the tutorials. The tutorial, the information, let's say whatever from the calculation, is it a program or is it data? Okay, so this is a program. Okay, program, you need to store in the program memory. Okay. Okay, again, I've give very simple descriptions of this. Program memory means something that's generated while running the sequence of the logical sequence. Data memory means something that it's being programmed. Okay, data expected, the portion of memory used for storing variables and data expected to change during, so it needs to be easily modified. So this is one of the example, variable. So variable, when you program it in C, you do not see the variable, but the compiler allocates a memory for this variable, so it needs to be easily modified. So you need to use the right memory for this kind of system. Okay. Now, of course, data memory and program memory, okay, they are two different things. One is for the program and wait. Okay. So program memory is memory that's run for during the program execution of the program. Data memory means something that you write, a program, program that you write in C programming, you compile it, and then you store it as a data memory. Okay. Now, this guy here is one of the most smartest people that I've ever known. Okay. The contribution of this guy in the computing world is mind-boggling. Okay, so this guy has this guy called von Neumann. you can see his name anywhere. Basically, computer textbooks, any computer field is based on this guy called John von Neumann. His contribution in mathematics, in logic circuits, in whatever, practically this guy is actually a mathematician that eventually contributed a lot in the area of computing. Now, of course, this guy came up with the early versions of computer. This guy is also one of the founders of, together with Alan Turing, these few guys created the whole world of computing and eventually artificial intelligence. Some of the stuff that he wrote eventually became the foundations of artificial intelligence. So two architecture, computer architecture actually came about. The first one is what they call von Neumann, referring to whatever that this guy designed, and the other one is called the Princeton architecture. So this Princeton architecture came out from, if I'm not mistaken, from Harvard. All right. So you have the von Neumann and you have the Princeton architecture. So this Princeton architecture is developed by a group of people. Von Neumann architecture is practically the early versions developed by this this guy called John von Neumann. Okay. Now I'll jump straight into what it means. Okay, so that you can actually read for yourself. Now this picture represents whatever that I want to talk about. You know, the first block diagram represents the von Neumann, and the second one is actually the Harvard architecture. Okay, I'm sorry, I think I might have confused you. The first version is called von Neumann architecture, and the second one is called the Harvard architecture, not Princeton architecture. Okay, so the first one, there's only two categories: von Neumann / Princeton, because that is where he taught as a professor in Princeton. The other one is Harvard architecture. I'm going to look into what is the difference. Okay. Now, in the first configuration, the data memory and the program memory are accessed together using a common bus. All right. So you can access CPU talks to the memory, whether it's program or data memory. There's no difference, no distinction. They are the same. Okay. But in the Harvard architecture, it's different. Separate data bus. So you have address bus or data bus for program memory, and you have your data bus for data memory. So it's separated. Now, most of the systems today actually uses the Harvard architecture, unless there is a very specific application you want to use data and program memory. Now, what are they? What type of applications would actually use a von Neumann architecture? You might consider, well, it's very weird. You know, why would we want to combine both the program and data memory together? Well, there is a very specific application. In a case where you want to change your program codes on the fly, okay, you've done your C programming and you want to change some of this program code on the fly. So in this case, von Neumann architecture would be a better solution. Okay, you can seldom people do something like that. You write a program and you don't want to change the program. It keeps on running forever and ever. But in the case where you want to change program memory from, let's say, your program write from an OR operation, you want to change it to a XOR. Okay, based on whatever the memory is writing. In this case, this is good to follow the von Neumann architecture. Okay, other critical component on memory map. This is what we call memory map. Means to say, memory map means how can I actually access the memory? Is the memory fully accessible, or there are plots of memory that I cannot touch? Okay, so this is what it means by your memory mapping system. Okay, can we access any single memory, or there are plots of memories that are reserved? You know, they are means to say that the numbering of the memory. You can see in our previous example. Okay, we have numbers for your memory, F81E, and they are sequentially arranged. So this is what we call memory map. Can the memory be sequentially addressed, or it's just cluster. Okay, certain memories from this region to this region you can access, and then certain memories you cannot access until you reach a certain region. So this is what we call memory mapping. Okay, how you map the memory. Okay, so this is useful. It's a model representation of a usage given addressable space of a microprocessor-based system. Is useful for program planning and selecting the proper microcontroller for application. Now why is this important? Bear in mind when you're doing program, right? Sometimes your address can be indexed. Let's say, for example, F189. After you do this, you go and access the next section. You just +1 to the address, and you access the next memory slot. Okay. Now, if your memory map is fully accessible, you can do something like that. But if your memory has cluster of memories that cannot be addressed, then in this case you cannot do the indexing for the memory. Okay, you cannot use a flow loop, you know, +1 to address every single memory. You have to know this memory from this memory is accessible, this memory from this memory is not accessible. Okay, so we call this the global and the partial. Okay, global means memory system that you can address 100%. Okay, means to say that you can just sequentially move using an index. But partial means certain portion of the address you cannot access. They are not sequentially numbered. All right. So this is something that you need to look into. They're also very important. Okay. Now this is an example of. Let me see. What is the example? Global and partial. A is global. B is partial. Okay, as you can see, certain part of the memory are connected to hardware. So in the B side, certain things that you cannot touch because they are attributed to parallel port and all these kind of things. But in the global side, global memory side, you can see that they can be sequentially used. So this one is something that you need to understand the memory architecture. This one is you can assume that it goes from memory to memory and from memory to memory. Okay, so they're divided in such a way, okay, where you can actually access it sequentially. Whereas this one is a bit weird. They are, you know, certain parts are used for certain things and so on and so forth. Okay. So I think that's all that we want to discuss on memory system. More important, Endian C. See, a simple story has actually evolved into a computer term. Okay, so Endian C and the memory mapping. Go and read more on the textbook. So I think look forward to the labs. Again, the first week of the lab will be a bit uncomfortable because it's the test and trial version. So I hope that any problem you can send an email to us. We will try to solve your problem. I understand that some of you have problem with assessing certain things. Like for example, some of you, for certain reasons, you cannot access Moodle or whatever. Please let me know this situation so that I can assist you. The accounts problem and the monetary issues for the university is not so much my concern, but it's more, my main concern is actually delivering a good lecture. So if there's any problem, a bit of feedback will be useful. How can I further assist you? Okay. If the internet problem, some of the places I understand, some of you are international students, you have internet problem. Even in Malaysia, some of the spots you have internet problem. Please let me know. Discuss with me. How can I further help you? I think with that, I would just like to end my lecture today. Today we discuss on the memory system. Various stuff on the memories. Go back and read on NDNC. Okay. So I think that's all what I want to discuss. I hope you have a good day, and I see you soon next week. Okay. So check out my tutorials, which I will prepare. I will upload it on YouTube as usual. All right. So I'll see you guys. Bye bye.